Hi guys, thanks for having me. Thanks for coming today. I'm Igor, I'm a senior backend developer at Mobfox, and today I will tell you a bit about how we not process 30 million requests per nanosecond, but actually how we process them per minute, and how we actually learn from that data and do some decisions in real time. So let me actually start with what we actually do and why we need to process so much data and why we have so much data. So we are in this business called programmatic advertising. So what does programmatic advertising mean? It just simply means that ads are not sold by humans anymore, they are sold by machines. So if you imagine you have a mobile app, and this mobile app would like to show an ad. And to do that, they simply call our service, and what we do is we stage an auction between a bunch of advertisers or companies representing advertisers, and they bid on this, and they say how much they would want to pay for showing their ad in that app. And the winner, the highest one, then gets selected, and we pass it back to the app, right? So essentially, we are kind of a man in the middle, a service between the app developers, mobile app developers, and advertisers. Sounds simple, right? But actually, it's not that simple, and it's not that simple because we have some very nasty constraints. So we need to process each request actually under some very tight time constraints. And that number is, on average, around 300 milliseconds per request. So if you imagine this auction selecting the best ad, the most expensive ad needs to happen in 300 milliseconds on average, right? And the reason for that is simple. It's because when it happens in real time, you know, when someone loads an app, opens a view, when the content is loading, there is already an auction happening behind, and the ad gets selected. And we don't want to block that, so we need to really be fast. And to make things even harder, or more interesting, right? So we need to do this many times. So at peak time, we need to do this in 30 million times per minute. So if you do some math and you sum it up, you come to around 2 billion per hour. And the reason for having that much data is actually, if you imagine all those requests that hit our app partners or apps actually get sent to us as well. So all those big apps, or some of them, they send requests to us as well, and we actually get all that traffic. So it's not easy, right? But it was not always like that, so the numbers actually grew a lot in the last years. And let me tell you a bit about how it started, right? So Mobfox started in 2011, and back then it was still a startup. And it went through this usual or a common startup roller coaster. So, you know, there was a one man developing it, he was doing both back-end and front-end, and he was just a single guy, right? So he did not need any version control. He was just changing files on production directly, editing it there. And he was using PHP and in places where he shouldn't actually use it, right? It was not the best fit for the problem, but he was still able to do it. And on top of that, the code was not the best. So the code really did not have any indentation, and it didn't have any exception handling. And worse of it, there was no monitoring of the system, so you didn't really know if things were working correctly or not. But on the other side, not all was bad. So the service was already making money. So he had like a lot of apps using it, and he already had a lot of advertisers on board. And of course, at the end of the month, he was already making millions in revenue, seriously. That's not a joke. And he was soon able to open up offices for the company in London, Paris. He had one in Vienna already. And the outlook was even better. So it was this huge growth in the mobile market. So the potential was high for this company, for this startup. So it didn't take that long. And the company was actually acquired. He exited to a multimedia company called Matomi Media Group, so Matomi. And they were already a big player back then in the advertising domain, so they had a lot of experience, they had a lot of connections, and they grew the company even more. So very fast, actually, the company got into that numbers that I was mentioning before, and it needed to solve that problems with those big numbers. And if you guys were already here last year, or if some of you were, then maybe you saw our talk, and we were talking about how we solved one of those problems. So we talked about how we were able to go away from PHP and start using RxJava and Vertex for asynchronous processing of requests. But this year, we will actually zoom out a bit, and we will look on a different problem from a higher level perspective. And actually, let's go into that, right? Let me give you some intuition, actually, about that problem. And to do that, I first need to explain you how this add request looks on our platform, right? So imagine there is an app like Talking Tom or Shazam or Viber. So by the way, those are some of our customers of the apps using us. So let's imagine they call our add request API. And they say, OK, I want to show an app to that user. So what we do is we actually send this request, so this data, out to advertisers, to a bunch of them. And we ask those advertisers, are you interested in bidding on that? So do you want to show your ad in that app? And they can decide, yes, I want to, and send back an ad, or they can say, no, I don't want to do it, I'm not interested. And we collect these responses of them, and we pass back this information, we pass back the winner or no winner to the app itself. So if you look at this picture already, right, you can see there is an asymmetry happening. So on the left, we have one request going in, and then we fan this out to many advertisers. So we are on AWS, so if you think about it, right, you have to pay for the traffic you generate. And that is the traffic we generate. So we send this out to our advertisers. That's what we have to pay for. And OK, looking at one request, not that bad, right? But let's look at more of them. So we said we get 30 million coming in. So if we multiply this, it means we send almost 500 million requests per minute going out. So you can imagine this traffic really costs some money. It's not cheap, so it really costs a lot of money. And if you can be smart about it and optimize it and not do this traffic all the time, then you can save a lot of that money. And let's look at like an imaginary example, how you could do that, right? What you could do to save that. Imagine there is like a coffee lovers app. And this app, so the advertisers have figured out that if they show ads in that app during the night, no one will click on them. But if they show them early in the morning, a lot of people will click on the ads, right? So they have just decided that if that app calls us and then we call them for ads, and if that happens during the night, they simply won't bid. Why would they bid if their ads have no engagement? So you see, that's actually very useless and very expensive. So what we do is we send all those huge traffic out, but we don't get anything in advance. So if we can be smart about it and actually predict that this will happen so that they won't bid on it, we can completely skip that part, right, for those requests, and we can just send back immediately without going to third parties that, hey, there is no ad for you. And this is actually what we will talk about today. So how to achieve that, and what benefits this brings is that we save a lot of money on this traffic out, and on top of that, we also process those requests much faster. So I mentioned before that we need 300 milliseconds on average for each request. So if you can skip going out to third parties, you can actually process those requests in 50 milliseconds already, so much, much faster, meaning that you can process more requests with the same amount of servers, and again, you save money. So it looks very good, right? But there is a slight trap in there. So it's not all that simple, you know? It's not like the advertisers say, OK, I will bid on that app during the night, or I won't bid during the night, I will bid during the day. Their behavior is actually changing much more frequently. So it changes from minute to minute. And for that, actually, you need to be very responsive. So you need to learn on this behavior from minute to minute and be able to adapt to it. And the question or the challenge at the end of the day is actually, how would you decide on which ad request the advertisers will bid in the current minute? So how would you know that? And to make it even harder, how would you know that under a huge traffic load, so the load that we have? And actually, I'll answer this question soon, and the answer is actually Sparka. So if you know Sparka, or if you don't know Sparka, or if you ask yourself, what is actually Sparka? So I can tell you, Sparka's not that, right? It's not this funny-looking ball from IKEA. I mean, it is that, right? But we don't have that in mind. So we have something else in mind. And in our case, Sparka actually comes from the technologies that we use. And it was born in our office. So we had one of those discussions, and we were pronouncing those technologies. So one was Spark Streaming, the other was Kafka, and then the word Sparka came out. And since then, we use it. Hashtag Sparka, hashtag Mobfox. And let's have a look actually on how we use this Sparka technology, or Sparka and Spark Streaming and Kafka, for solving that problem from before. So, like every master plan, right, or like any good solution, our solution consists of 3 steps as well. And we even went a step further. So we figured out the missing part, so the second step. And I will be explaining each of those steps to you today. And I will first tell you how we learn this advertiser behavior, so how we collect this training data that we know when the advertisers are willing to bid or they are not, how we then engage Kafka and Spark Streaming to process that data, and finally how we profit from that data and from the decisions that we make. Actually, that is not the only optimization that we do. So the approach is very similar to many of the optimizations we do on at Mobfox, and all of them follow a very similar premise, so a very similar pattern. And the pattern is actually that you have this huge traffic going in, and you split this traffic in 2 parts. And you take like 10% of the traffic, and on that 10% of the traffic, you won't apply any optimizations you would like to learn from that traffic, and then you apply the optimizations to the rest, to the 90% of the traffic. And actually, that's a very important takeaway. So if you do some learning on some data on some of your traffic, be it machine learning or whatever, you should never learn on the traffic you optimize, because then you influence yourself, and it's not good. So we have this 10% in our case for learning, and what we do is actually we get those requests, right? They hit our auction servers, and then the normal auction happens. And while this auction is happening, something else happens as well. And what happens is we actually collect some metadata about each request. And this metadata contains some information about the request, and if this request got an ad or if it didn't get it. And we dump this metadata in Kafka. And so what is Kafka, right? Anyone knows Kafka? How many? Okay, quite some, nice. So briefly telling you, so Kafka is like a very high throughput, low latency message queue, right? You can imagine it for the sake of simplicity like that, and it has some of the nice features, so it partitions your data, it replicates your data, meaning you can very easily horizontally scale. If one node dies, another one takes over. All of it is very easy, right? And we use it as a message broker between these auction systems that we have and the system that we use for learning, for training a model that will decide. So we can skip to the second step, right? To the interesting one, so how we process that. So we have Kafka now. Kafka is this message queue that has the data dumped in, and then we have another thing, Spark Streaming. How many people? Okay, not that many. Okay, I will tell a bit more about it. And then we have Spark Streaming, and you can imagine Spark Streaming, again, as a very high throughput and fault-tolerant system for stream processing. So what is stream processing? It means you can process messages in real time. So they are coming in the system from somewhere, and you process them, do something with them, and then you save the results somewhere. So let's dive in a bit. So let's have a look at what this actually means on some of the internals. So on the left, we have our Kafka cluster, right? Does this work? Yeah. So we have our Kafka cluster, and we have the training data in here. And here we have the Spark Streaming cluster. And the Spark Streaming cluster, we said that it streams through the data, so it reads the data continuously and processes it. And it's actually not really continuously. It's a bit more discrete. So in our case, it happens actually every minute we want to process some data from Kafka. So every minute one of those such micro batches will be started. This micro batch is actually a Spark job. So one of these micro batches is started, this job is started. This job will read the data from Kafka, and it will process it and save the results, right? And then, okay, it will do that maybe in 2 seconds, and then it will wait for another 58 seconds, and it will start another one. And you don't have to do anything. It just happens automatically over and over again. And it's very stable, and it's fault-tolerant, and it really can handle a lot of data. And in our case, how this happens is actually like that. So We have our data in Kafka, and in Kafka you said you know it, right? You know this high-level abstraction in Kafka is a topic, so you save your messages in a topic. But you probably also know that Kafka doesn't do any management of this, how much your consumers have read. So you have to offload that to your consumers. But Kafka at least offers you some kind of a metadata store, a mean for saving what you just read, what your program has read. So this is this consumer offsets topic since one of the earlier versions of Kafka. And you can use that one to look up what data you have processed. So, OK, we have our Spark streaming job, right? And we are one of those Spark batches. And we want to see now how this batch will process that data from Kafka. And very important for you to remember is that each Spark job actually has two important bits. It has a driver. This is somehow like an orchestrating part. This driver will bootstrap your workers or executors, and then those executors will do some heavy lifting, some processing, and then you can do something with that data, right? So let's have a look how this works for us. So our driver actually just reads the offsets from Kafka. So it doesn't directly read the data yet, it just reads the offsets, what data needs to be processed in this micro batch. And once it has that data, it starts the executors. And this is actually a very nice step because you can have many of those executors, and this is where your application scales, right? So if you have more data, you just have more of those executors, and then each of the executors itself will read the data from Kafka, from this topic with the data from in our case, it's called call-out optimization because we want to optimize calling out. So these executors will read this data, and then it will do some processing on it. And so what does it mean, processing? That's arbitrary. You can map it, you can reduce this data, whatever you want to do. What we actually do is, for each request, we have a look at how many ads it got, or for each type of request, how many ads it got. And if the number of ads in the last minute was below a certain threshold, let's say 1%, then we simply will mark this request as not being worthy to send out to advertisers. So we'll mark it somehow for being throttled, and this is actually our solution, right? So each executor will get this request that should be throttled, and it will pass it back to the driver, and then the driver will be responsible to actually saving this state somewhere. And I'll tell you soon where this state gets saved to, but you can imagine it's somewhere right now, and once it's saved, we also commit these offsets back to this Kafka offset topic, right? So that the next micro batch will start from the next interval, so that it won't process the same data twice. And Kafka can give you this nice exactly once semantics, meaning that you will process each message exactly once, not less, not more. OK, so we have saved this state somewhere now, and let's have a look where we save it. So in our case, we're in this phase 3 now. We want to profit now from this data that we saved and from these optimizations. And in our case, we saved this data in Aerospike. Do you guys know Aerospike? 1, OK. You don't count. 2, OK. Anyway, so Aerospike is something like Redis. You can imagine it like Redis. So it's a distributed key value store. It's very fast. It stores its data in memory. It stores it on SSDs. So you can actually can tell you how fast it is for us. So for us, like the P95, so the 95th percentile, when reading this data would be 400 microseconds. So below half a millisecond. So 95% of requests are actually handled that fast, the reads. So what we actually do here is we have the segments that we want to not send out to advertisers. We have them in this key value store. And on each request out of those 90%, before sending this request out to the advertisers, what we do is we simply check this internal store and see, should we send this request out or not? And if the answer is not, then we have saved a lot, because we just went to this internal store for that request instead of asking, I don't know, 15 advertisers. And OK, you ask yourself, all right, so you in some segment in some parts of your traffic, you save a lot of requests. to outside advertisers. But then again, on each request, you need to go to this key value store, which also brings some overhead. And we are actually even here a bit smarter. So what we do is, we know that we process this data only once per minute, so we don't have to go actually to Aerospike on every request. It's enough to actually go once per request per minute. So, and then we can cache it locally on a server for 1 minute and reduce the load even further. And then, yeah, this is actually how we profit, right? So the question now is, how much do we profit with it? Is it even worth doing all that, adding that infrastructure, doing all that processing, maintaining that? And I can tell you it is worth, right? So in our case, the savings are around 20% of traffic out. And I can tell you, so we process around 10 petabytes of data per month. So 20% of that would be 2 petabytes. 1 petabyte is 1 million gigabytes, to give you some scope about the number. So the savings are actually at the end of the month are between 20 to 30K. So it's not peanuts. It's a nice number. It's worth doing it. And on top of that, I have mentioned before, right, that we can shorten the request time for those requests. And we can shorten it from the usual 300 milliseconds on average for those requests. We can process them in 50 milliseconds, so much faster, which again means that for the 20% of the traffic, we can work much faster and handle more requests. And this is actually not the only optimization we do at Mobfox. We do many more. So we have another optimization where we try to predict the prices that the advertisers are willing to pay for ads, and we help our apps or publishers make more money with that. And then we have another one where we find out which advertisers are having like problems with timeouts right now or have busy servers, and we try to throttle them. And then we have another one where we match like these apps that want very fast responses with advertisers that are able to respond very fast. And there are more and more that we plan to implement, right? And guys, even though we are hiring, forget that we're hiring. So if you just want to talk about what I've kind of outlined today, right now here, please come to our booth. It's just around the corner here. And we can talk about either the backend technologies, so the stuff that I explained today, or we can, if someone of you fancies front-end, we can talk even about that. And the booth looks like that, so you can find us here, right? That's us. And you can even play some basketball. So we have a hoop, and you can shoot some balls, and you can even win a fidget cube, or you can win one of those pop sockets. And we had, so in this, if someone was already at our booth, we had like a lucky draw, right? We are giving away a drone, and you were able to submit your name in there, and we will actually now announce who is the guy who will get that drone. And I won't make it dramatic because I'm not running out of time. I can be a bit dramatic. No, but I won't be. OK. So without further ado, and the winner is Joachim Šiškovič. Congrats, man.
Thanks.
OK. So it's yours. Officially now, you're the lucky winner of the Mobfox drone.
Thank you very much.
And I think we can make a photo with the crowd.
Let's get him an awesome memory, make some stuff. I make a photo with you guys, okay? Come on. Turn around, turn around.
Ah, just like that.
Okay. Thanks, guys. Peace.
Thank you.
Don't leave the room, we have questions. Sit right down again. Thank you very much, Igor. That was really good. I mean,
thanks.
That was very fast. I mean, you have so much information there. It's good.
Too much.
But we have some very good questions, so I won't talk too much and we'll get straight in with them. Do you have something on GitHub we can look at?
We have it, but it's not public.
OK. But they can come around the booth and talk to you about... Be quiet when you're leaving the room.
They can.
Where people are listening here. Good, good, good. Yeah, there's a few questions in here about the auction process.
Yes.
let's take this one first. Yeah, how do the advertisers decide if they want to bid? What about the metadata that goes to the advertiser?
So they get, like the information they get would be from what country the request comes, what device he's using, what kind of request is it, what kind of app is it a sport app, or is it, I don't know, a news app? So there is even some information about the user at the end of the day, so if he's a male, a female, the age of it. It depends on the app. So what the
GDPR?
Yes, it's coming.
It's what do you mean it's coming? It's next week.
Yeah, I said it's coming.
Yeah, okay, it's coming. Okay.
Yeah.
Okay, you heard it here first.
So yes, and based on that they decide actually, and they have their own logic, and it's not really the advertisers, right? I simplified it a bit. Those are similar companies to us, but we are an SSP, so we represent the publishers, we represent those app developers, and they represent the advertisers. So they're called DSPs, demand-side platforms, and they have like smart logic algorithms, and they kind of time what ads they would like to show when.
But your pitch to the app producers is that they can make more money if they use you.
Yes.
Right. Good. Why not Kafka streams?
We started back then with Spark Streaming, actually. We were considering Kafka streams, but back then they were not that stable yet, and they didn't get that much traction yet, so it was just a decision based on the information we had back then. And we are actually still considering to implementing some of the newer of those workflows with Kafka streams, because there is some nasty stuff with Spark Streaming, so it's very hard to develop it like locally, set up a local cluster for experimentation, and sometimes it's very hard to debug, so you get some very cryptic messages, and we're actually not sure if Kafka streams help a lot, but it's at least worth trying it out. It wasn't really, we didn't try Kafka streams before, it was just a decision back then.
So it's not a religious decision. What do your clusters look, or what does your cluster look like?
So they run on AWS. They're Dockerized. So I think right now we have around five brokers or something like that. But they're Dockerized. So on AWS. So no bare metal.
Okay, no bare metal. Yeah. Do you plan on using machine learning or AI for this optimization?
So not for this one, but we have a different one. Like I said, we do this price optimization, where we try to kind of estimate how expensive the advertiser thinks this ad space where he wants to show his ad is. And in that one, we actually use some pretty basic machine learning. So we use decision trees, and we actually segment the advertiser, saying, okay, if the country is that one, if the device is that one, right? Austria and iOS use that price, otherwise use the other one.
So there's another question here. Why do you have to bid on ads in real time? Isn't it like the more intelligence you gather about the users and the auctions, the more you can predict? I mean, that's what you said. You can predict what's going to happen. So don't the auctions become less important with time?
No, they don't. I mean, you cannot reverse engineer all of it, right? There's always some information that will leak around it, right? So if we would be able to like perfectly reverse engineer all the DSPs, right?
You'd be the advertiser.
Yes.
Yeah.
I mean, and you would just simply ask the one and not all of them, right? Just the one who you would know that will bid the most. So
that's like chicken and egg. I mean, if you do all of that work, then you become the advertising provider. Probably you don't. Well, it could happen. You see the way he answered there. It could be. Let's get two more in. The time is running out. You all need lunch. What are the server resources you have? Can you give some numbers to the people in the room?
We can check this later on. I don't know it by heart right now. So if you can stop by our booth and we can have a look at that.
Let me just fire in one of the questions, which is further. I like this one here. How much legacy PHP is left?
Is this someone from you guys?
Yeah.
No, I think it's around 15% right now. 10 to 15%.
You asked that. You're getting questions from your own colleagues here. You do know that.
They sabotage.
They don't know. He doesn't know what you do.
No, I think it's not that much actually anymore. So it's around, I would say, below 20%.
Okay, I'm just looking at the other questions further down. The CDN. Any other languages for the engineering? What's it look?
We use Python in a part of it. So mostly because we have some tools that are written in Python, so we have like an aggregation pipeline, and that one is written in Python, sorry.
Okay, last one. The 300 milliseconds, how did you get there?
It's a requirement. So it needs to be fast. So how do you get there? You have to have a very fast infrastructure and nice water.
So what are the key variables then that you have to consider getting there?
So actually, you have to get there. You have to be able to asynchronously handle those requests, right? You cannot afford to handle each request on one thread, because then you would have too many threads on your, and that was actually the problem with PHP, right? And that's why we switched from PHP to Vertex and RxJava, because you can do this much more efficient there. So that would be the key thing here, yeah.
I think that's all pretty awesome.
And it is chosen randomly, yes. The next one.
Okay, the next one. He's on fire here. I mean, it's the 10% traffic. You just want him to carry on all day, don't you? I mean, we have to have lunch, man. I mean, okay, is the 10% traffic just chosen randomly? Yes. Which CDN you sort of had that, didn't you? AWS?
I think something from Amazon, right?
Yeah.
Yeah.
Something from. Okay, I'd like to wrap it up there. Say thank you very much to Igor. A big warm round of applause.
Thank you, guys.
Great. We'll see you when.